Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's begin chapter 3. Chapter 3, this first lesson is going to revisit those tile patterns that were introduced in that first chapter. And this is the beginning of us starting to look at two variable equations instead of one. We spent a majority of 7th grade and all of last chapter working with solving problems that had one basic variable like x, and then learning how to simplify and how to work in those situations to find out the value of x, okay, find the solution to the equation. Now we're going to have two variables. We're going to have what's called an independent and a dependent variable, and we're going to see how we can use algebra and other tools to try and solve problems or make predictions and draw conclusions about situations where one of these would affect another, okay? So a couple of terms for us to look at to begin with is the term relation. When we're talking about a relation, we're talking about a comparison of two sets of data. And the relation can be displayed as ordered pairs. So you might have two sets of data. You might have like time of day and temperature, like the number of hours, afternoon, and the temperature on a daily basis. And we can look to see if there are trends as to whether or not later you get into the afternoon, does the temperature tend to go up or does it tend to go down? What seems to happen? Is there a correlation between those two sets of data? And those sets of data generally are going to be numerical, which means that we can put them into ordered pairs, and we can plot those ordered pairs on graphs, okay? So this has nothing to do with my random example of temperature, you know, afternoon or whatever. This is just random points, okay? So a relation is just a set of data. So here's our x data, here's our y data. We put pairs together and it can be plotted on a coordinate grid. And what we are going to learn throughout this chapter and later on in this year, especially in chapter 7, is that if you look at the shape of the graph and how it's flowing, you can make predictions. You can draw some conclusions about the relation that you're working with, about the set of data. Okay, so when we refer to a relation, think of like a set of points on a graph or a set of ordered pairs in a table. Okay, so you've been learning how to work with variables and how to find values of variables in equations. In this section, you will learn how to extend patterns and how to generalize your pattern with a rule. As you work with your team, or as you're working at this at home, use these questions to focus your thinking and your ideas. How is the pattern growing? What is the rule? Not all relations have a rule, by the way, but we're going to be focusing on ones that do. Is there another way to see it, and how can you tell if your rule is correct? Okay, so this particular problem has two different examples if you're in the online book, but we're only going to work on A. If you choose to work on B and you want to contact me to see if you're getting it right, I'd be happy to take a look at your work. But you know, we've got a lot. It's hard to get a lot of these math problems in during the school day, and doing two of these is not necessary. We can just work with one and get the basic point of this. Okay, so some people describe mathematics as a study of patterns. For each tile pattern below, draw figure 1 and figure 5. First try it individually and then consult with your team. Well, you're not going to be able to consult with your team, but what you are going to be able to do is pause, and then you'll see what I come up with, and we can compare and see if you're on the right track, okay? And then what does figure 100 look like? And nobody wants to draw figure 6, 7, 8, 9, 10, all the way up to 100, right? So we want to generalize. We want to see, how is this pattern growing from one figure to the next? What happens and where does it happen? Okay, so first thing I want you to do is pause the video And I want you to draw figure 2, figure 3, figure 4, and label them. Okay, make sure I'm going to call this the tail, I'm going to call this the row, and I'm going to call this the column. Now, as you are counting the tiles, you might want to consider when it grows, going from figure 2 to figure 3, where do you see the growth happening? How many tiles are added on to the tail? How many are added on to the row? And how many are added on to the column? Okay. And it's also a good idea to do counting, like how many tiles are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? Let me count it again. 1, 2, 3, 4, 5, 6. Oh, it's 9. Okay, I got to count it one more time because I've gotten 2 different answers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sometimes we make a mistake and we count this guy twice. We count it in the column and in the row. So there's a total of 9 there. Count how many are in this figure, how many are in that figure, and use that pattern of growth to determine, first of all, how many you think would be in the fifth figure if it continued with that pattern of growth, and how many, if you were to work your way backwards, should be in the first figure. And then look at it to try and figure out, okay, where are they being added on? So what would figure 5 look like if I added on those parts in the same places, and it excuse me, if going in the other direction you're taking away, then what would figure 2 most likely look like? No, figure 1. What would figure 1 most likely look like? Okay, so I'm going to pause it. You go ahead and pause and see if you can't look for the pattern, create figure 1 and 5, what you think they look like. And then this one might be the hardest part, is trying to figure out what the 100th figure would look like, but we'll do that together if you're not quite sure how to do that. But if you think you might know how to do it, go ahead and do it. And then you can always make your correction if you've got one of the parts a little bit off. Okay, so go ahead and pause. I'll pause. And then when you're ready, start up again. All right, let's see how you did. So first of all, I would just like to say one thing. Math, for some people, is a lot of fun. For other people, it's the worst thing in the world. Um, every student I've ever spoken to, including myself, who likes math, likes it because they treat it like a puzzle, and they like solving puzzles. They like trying to figure out what the pattern is, and try and figure out how to win that puzzle. And when we're dealing with this kind of algebra, what we're going to be doing over the next few days is very much like puzzle solving. So if you can think of it that way, you might get a little bit more enjoyment out of discovering, oh, this is the trick. This is how we do it. Now it makes sense to me. So give it a shot. Think about solving puzzles. Now, of course, for those of you that hate puzzles and hate math, I'm so sorry. Not much I can help you with there, other than hopefully after doing some of these activities, it starts to make sense and you appreciate how we can use this kind of a strategy to help us solve other problems and make your math easier in the future. So if there's anything making it easier for you is generally considered a good thing. So I hope you can embrace that. Okay, so what are we going to do here? We are going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. We already got that, right? So there are 9 pieces in there, and this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that increased by 4. Let's see what happens here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Interesting. Every single time it increased by 4. So where are those 4 where we increased? This is what I'm going to do. I'm going to go ahead and I'm going to take and I'm going to not, I don't care about coloring this in perfectly. I'm just going to make this so that I can take this imprint and place it onto here. Okay, so see where the 4 got added on? There looks like 1 on the tail, 1 on the column, and 2 in the row. So now let me go ahead and see if we get the same kind of growth happening on figure 4. Okay, so I'm adding these to the previous because that was the growth, And now let's move these guys over to here, and you see the same pattern of growth happening? We absolutely do. We see one on the tail, one on the top column, and two on this row. So when you draw figure 5, we're going to have to take all 17 of these tiles, add one more to the top, one more to the tail, and two more to the row, and that will give you figure 5. And when we work our way backwards, let me go ahead and I can get rid of this. When we go backwards, I believe we want this one taken away. We want those two to be taken away, and we want this one to be taken away. So this should be what your figure 1 would look like, with 1, 2, 3, 4, 5 tiles after those 4 have been removed. So what do I have here? What do I have here in the, is that figure 5? Okay, so let's start with figure 1. Right? That's what we think figure 1 should have looked like once we took away these two for figure 2 and that one from the top. So you've got 2 in the row, 2 in the column, 1, 2, 3, 4, 5. Right? That's what we predicted. And for figure 4, for figure 5, we had 1, 2, 3, 4, 5. So we'll want 6 on the tail. 1, 2, 3, 4, 5, 6. We had 1, 2, 3, 4, 5 in this column, so we want 6 in that column. 1, 2, 3, 4, 5, 6. And we had 1, 2, 3, 4, 5, 6, 7, 8 here, and we'll need to add 2 more at the end to make 10 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the prediction, if these are growing by 4, the next one, figure 5, should have 21 total tiles. So let's just go ahead and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've already counted this one, so we're going to move to this one, 13, 14, 15, 16, 17, 18, 19, 20, 21. All right, so now for the patterns of growth. Let me just pause something for a second. I'll be right back. Okay, so for the patterns of growth, well, no, not necessarily patterns of growth. For the total number of tiles in each section, I like to think of my 3 sections as you got a tail, you've got the column, and you've got the row. Okay, so it looks like if all of our figure numbers are always our x, right? Let's make x be the figure number. And y represents our total number of tiles. And we can break this up into little sections. For instance, the tail, if x is figure number 2, and this tail has 3 in it, then we can say that whatever our figure number plus 1 is going to give us the total number of tiles in that section, right? Take a look here. Our figure number is 3, 3 plus 1 is 4. Our figure number is 4, 4 plus 1 is 5. So that describes the tail. Now let's take a look at the column. Actually, no, let's do the row. I want to do the row first. The row has 4 in it, correct? This row has 6 in it. This row has 8 in it. Do you notice any pattern there with our figure numbers? Here, figure 1 has 2. Here, figure 5 has 10. What is always happening with our rows? We're always doubling our figure number for the number of tiles in the rows. And now the column. Now, keep in mind, I've already done this part. I've already done this part. So we're only counting this part of the column. I've already done this part. I've already done this part. So we're only counting this part of the column. I've already done this part, and I've already done this part. So I'm only counting this part of the column. So what do you know about the height of the column, the number of tiles compared to the figure number? It's always the same. So that means that the total number of tiles in any given figure number is going to be, let's combine like terms 1, 2, 3, 4 x's plus 1. So let's take a look at figure 5. That would be 21 tiles, right? Because 4 times 5 is 20 plus 1 is 21. Okay. So here we are taking these abstract pictures of algebra tiles, these figures, and we're noticing for a pattern of growth, and we're using those patterns of growth to determine a rule that's going to help us answer this question, or for any figure number. You know, we could do figure 1,322. How many tiles would be in that? Well, multiply that times 4, and then add 1, and you've got your total number of tiles. So what does the 100th figure look like? The 100th figure is going to have a tail that is x plus 1, so it's going to be 100 plus 1, 101 tiles. Then it's going to have the row, which is going to be twice the number of tiles, so 2 times 100 is 200, and then the column would be 100 tiles tall for a total of 401 tiles. And let's use our rule to see if we can verify that. 4 times 100 is 400, plus 1 is 401. Okay, so we are going to be doing a lot of this. If we're able to figure out what figure 1 looked like and figure 5 looked like, you are doing a great job. If you struggled with 100th figure, that's what I would expect. If you actually figured out what was in the 100th figure, you did brilliantly. Most people do not get this right away. It's something that over time you start to look at the trends and you start to figure things out. How am I doing on time? I'm doing a lot of talking. Let's move on. All right, this is another kind of a fun little activity. And this we generally do in our teams, and we do it together. I have 2 different resource pages you probably saw on Classroom, where you can print this off, or you can just copy these down. It doesn't really matter if you don't have a printer at home. You can just copy this stuff down. So you've got your inputs and your outputs, your x's and your y's. And so this is kind of like a relation here. These are all examples of relations. Now, relations, in this case, these are categorical or non-numerical types of relations. But when I create a rule for it, I'm going to kind of show you how we can make it sort of algebraic and numerical in a way. Okay, so what I want you to do is look at the evidence that's provided here and see if you can figure out what is the trend going from L to N, from W to Y. What is happening there with those letters of the alphabet? And once you figure out what's happening there, figure out what goes here, here, and here. And then you can, if you want to, come up with a couple of other examples. What's happening here between hot and cold, up and down? Do you notice a trend there? Go ahead and fill in those blanks. And if you want to add a couple of your own, you can. And then what's happening here? Oops. Doing a little color coding. So what's happening here between the number of sides on those polygons, between here and here? If you cannot figure out how to draw the shapes, but you know the names of the shapes, go ahead and write in the names. I did both, but this was an actual challenge. I erased so many times before I got it right. And then you can go ahead and if you want to create some extra ones there, you can. Okay, so pause and then fill those in, and then when you're ready, come back. All right, so what did you notice here? Did you notice, actually, let me write it down here, that Y is always 2 letters after X. So if we went through the alphabet, L, M, N, right? So you skipped over the M to get to the N. So this is 2 letters beyond. Same thing with W. We skip over the X to get to the Y. So that means this one had to be an A, because A, B, C. 2 letters before F would be D, and 2 letters after Q would be S. Okay. What do we notice about? Oh, and by the way, the rule that I write there is if you think about it in numerical terms, then Y would be equal to X plus 2, right? If X is the letter of the alphabet, 2 later or 2 after that in the sequence of our alphabet would be the next letter. So that's how I gave it a numerical type of a 2-variable equation. What's happening here between hot and cold, up and down? If you said that they are opposites of each other, you are exactly right. Y is the opposite of X, and X is the opposite of Y. So easy, and you could have chosen different synonyms for hard, difficult, challenging. You know, any word that means the same as hard would be fine. Light. Light has a couple of different definitions. You could have chosen dark, which is, I think, what I chose. Or if you thought of weights, you might have said heavy. As long as they're opposites, that's fine. And then left and then right seems like the obvious. So in numerical speaking, when you take the opposite of something, it's like negative x, right? The opposite of x is equal to y. And what do we notice here between the side lengths, or not side lengths, but the number sides, a triangle and a pentagon? This has 2 more sides than that. The octagon has 2 more sides than the hexagon. So here's another one where you've got your x plus 2, and the shape, the polygon in your output, in your y's, is always 2 more sides than the polygon in your input, or your x. So pentagon, this is called, when it has 7 sides, a heptagon, and good luck making that drawing. And then this is a hexagon, so this one I could do, so this is pretty easy. That's a square. And then hexagons and octagons, so an octagon, what has 2 more sides than an octagon? That would be a decagon, and that's another one that's not real easy to draw, but it can be done if you put your mind to it. All right, now we're going to speak numerically. In these situations, something has happened to x to get it equal to y. And I used to play this game called a game with Function Bob with 5th graders that I used to teach, where they would try and figure out the rule of what you're doing to x to make it equal to y. And that's essentially what this game is right here. And there has to be one answer that works for all of them. For instance, if you said 8 plus 9 was equal to 17, then 10 plus 9 would equal 19, but that's not 19, so that's not the rule that works here. You've got to think of a rule that works for all of them, okay? Same thing here. You can't say 100 minus, color code. You can't say 100 minus 49 because that does not happen here. We're not subtracting 49 from 6. So what appears to be the pattern there? And then here you take 4 times 4 is 16, but negative 1 times 4 is not positive 1. So something else is happening to the x value to turn it into the y value. See if you can figure that out and fill it in once you identify what it is, and see if you can also identify the rule and write it as a 2-variable equation. All right, let's see how you did. We've got, here you got an 8, and adding 9 to it did not work. So it looks like if just a straight addition or subtraction pattern doesn't work, then there's always going to be some kind of a multiplication process. So I would start by multiplying this number times 2. And when you multiply times 2, it doesn't give you 17, right? But each one of these, after multiplying those numbers times 2, ends up being 1 less than y. So what if we said double this number and then add 1 to it? So 8 times 2 is 16, plus 1 is 17. 12 times 2 is 24, plus 1 is 25. 10 times 2 is 20, plus 1 is 21. So that ends up being the rule. It worked for all 3 of them. So now we take that rule and we picture plugging in the negative 2 here. So what is 2 times negative 2? That would be negative 4. And negative 4 plus 1 is negative 3. So this number should be negative 3. And now when we work in reverse, if we're saying that 9 is equal to 2x plus 1, that means that the 2x's before we added the 1 must have been equal to 8. And what number do you multiply times 2 to give you 8? This number must be the number 4. Okay. Now, if you want to create your own, you can say, well, what if this was 5? And this would have to be 10 plus 1 is 11, right? You could add any of those that you want to, but we'll just focus on these right here. So what's happening here? This is almost half of that. This is almost half of that. That makes me think there's a division process happening here, or maybe you're multiplying times a fraction. So if I take half of this and I add 1, I get that. Does the same thing happen here? Half of 6 is 3 plus 1 is 4. Yes, half of 30 is 15 plus 1 is 16. So I think we've got our rule. Now you could have said half of x or x divided by 2, and both of them would have been correct. If you had written it as y is equal to x over 2 plus 1, you get to the same place. So what's half of 4? 2 plus 1 is 3. And now let's work our way in reverse. This could be a little bit trickier. Let me clear this out. Okay, so for this one, our answer is 31. So I'm going to take 1/2 of some number, and then I'm going to add 1 to it. Well, if I take this 1 away, this must have been 30, right? So 1/2 of x should have been equal to 30, since 30 plus 1 is 31. So what number is, what do you take half of to get 30? You know what the most common wrong answer is? 15. Because people will take half of 30, but you're not taking half of 30. You're taking half of some number, and you get 30 for an answer. So this would be a situation where if we multiplied each side times 2, that would cancel out multiplying times 1/2, so x would have to be 60. So in keeping with our pattern, half of 60 is 30, and 30 plus 1 is 31, so our answer here has to be 60. How about on this one? Multiply times 4, no. Add 12, no. This is interesting. This number became a positive. This number was a positive. It stayed a positive. So we're not multiplying times a negative. It looks like 4, if you square it, if you multiply this number times itself, you get 16. And when you multiply that number times itself, you get 1. So I bet that's what the rule is here, where you're going to take the number and you're going to multiply it times itself. So what's 12 times 12? That would be 144. What is -6 times -6? That would be positive 36. And the answer, the most common answer people are going to have for this is 3 times 3 is 9. But technically, you could have also said -3 times -3 gives you a positive 9. Okay? So there we are looking for rules. And I'm going to make an executive decision here. I think, well, I don't know. I feel like we should be almost done. And if any of you want to continue practice, you should try and practice this. Okay, I'm going to pause. You spend a little bit of time. You've got this resource page. All I'm going to do is I'm going to do the reveal. Okay. I'm not going to go through and make this a 40-minute video by going through each one of these tables. Although if you have any questions, you could email me, you could contact me. But I think once you see what the rule is, it'll make sense, okay? So if you printed out this resource page 3.1.1b, go ahead and try and fill in all those blanks and figure out what the rule is. If you're just copying them down, go ahead and copy them down and fill in the blanks once you figure out what the pattern is for each one of these rules, okay? I will do the reveal. I'll start with the rule, and then I'll reveal each one of these boxes. There should only be one answer that works for all of them, so this shouldn't be up for debate, okay? Maybe the way that we write the rule might be a little bit different, but the rules will be the same, okay? So take some time doing that, and then I'll do the reveal so you can see if you got the basic trend here. All right, let's see how you did. Let's start. That first one was kind of tricky. This one, as you're going to find out, the ones that, where are you? Are you going to show up? There you go. The ones that have the 0 here, these are going to give you a clue about your hints. Finding out where x is equal to 0 can be very, very helpful, which we're going to find out more about as we move on through this chapter and in future chapters. All right, so what do we have here for the rule here? Turns out it was 2x minus 2, right? You double a number and take away 2. When you double 0, you get 0. Minus 2 is negative 2, which means that had to be 5. This one was negative 6. This one was 100. And this one was negative 1. For B, that one looks pretty straightforward. I think we're multiplying times negative 3 based on these two. Is that what it is? Y equals negative 3 times x? Yes, it is. So we've got negative 30, negative 2, 0, 12 should be that one. Yes. How about this one? Add 3? No. Ooh, that's a big jump there. I'm wondering, that went from 10 to 101, and it went from a negative to a positive. I bet if we square negative 10, we get 100 and then add 1 to it. I said I wasn't going to analyze all these, but I'm finding myself doing it because I'm a little math nerd. That's exactly what it is. So double it or square it and add 1. Interesting, you probably used a calculator for that, but maybe not. And then, of course, working backwards, remember, when you square a negative number, you get a positive answer, just like squaring the positive. So you could have chosen either 7 or negative 7. You could have chosen 6 or negative 6 for this one, and both of them would have been correct. Now for the last 3. For D, looks like we're subtracting. Oh, well, let's start with minus 6. That works. If it works for 2, it usually works for all of them. It does. It works for all of them. We didn't have to multiply anything there. We just took away 6. So this ends up being a 0. This ends up being 2, probably. This one ends up being negative 13. Yep. And this one was 46, and so on. Okay. What about here? Are we adding 4? No. Ooh, that's another big jump. That makes me think we're probably squaring again. But in this case, what do we square that number, so that's 4. So 4 plus 2 is 6, but that becomes 16 plus 2 is 18. So that's not going to work. That's the clue right there. When we square it, we get 100, but it's 110, so we also add this number on, right? So you take this number and you square it, and then you add that number again, and that gives you your output. So that's going to be x squared plus x. Or I suppose you could write it using this distributive property thing where you multiply this number times itself plus 1. So 10 times 11 is 110. 4 times 5 is 20, and 2 times 3 is 6. So you could have written that either way. So this ends up being 9 plus negative 3 is 6. And then you work in reverse. That one could be a little tricky. Let's do a little guessing and checking. Is that 5 squared plus 5? Yes, it is. And then 1 squared plus 1 is 2. And then the last one, that times 5 plus 3 times 5 plus 3, that was too easy. 5x plus 3. And so negative 40 plus 3 is negative 37. 0 plus 3 is 3. And then something doubled plus 3. What could that have been? 4, 3, 3 doubled is 6 plus, no, it's times 5, isn't it? Oh, it's going to be 1. And then 19 is 95 plus 3 is 98. All right. So, yes, I was afraid it was going to keep going because I can't help but explain things. But yeah, just looking for patterns of growth, looking for trends. What do you do to this to make that? Does it work with multiple? Does it work with all of them? Because if it works with some of them, it should work with all of them. And that whole idea of generalizing a relation with a rule and then using that rule to find any other piece of information is what this chapter is about. Okay, so go ahead and transition to the homework. You can clean this up if you need to clean it up and make a few corrections. And then always make sure that you're copying the tables down, you're showing your work, so that when you check your homework and you make a mistake, you can figure out what the mistake is and correct it. All right, take care. Bye.
Hey, feeling good. like I should. When in dark, walk